Okay, so we finished the first part of today by just checking power counting and normalizability, right? We just checked the dimension of the coupling, we saw how loop order grow, and that's what we found basically. Now, of course, we can really try to understand what we should expect at one loop. We already know actually the answer because yesterday Anna told us something. In the case of, for instance, she saw the explicit example with matter with the two external graviton lines and one loop of matter. Here we can do similar thing also with the just gravity, and we can go a bit more into details of discussion of the discussion of counter terms and so on. Let's do that. As I said in the first lecture, when we have perturbation theory, we can encounter divergences in loop integrals. And of course, we need to use some regularization method, usually to isolate the type of divergence that we have in the integral. And there are different methods. Once we isolate this divergence, we can like absorb this divergence in some redefinition of couplings, masses, and fields with wave function normalization of the Lagrangian, of the Lagrangian. And so before we start, we should say which regularization method we're going to use. We will always think of dimensional regularization. And in dimensional regularization, all type of power law divergences do not matter. The only one that matter are the logarithmic divergence, which means all integral that go like this. So you have like 0. So if you think of like having a cutoff here, you will have some contribution of this type. Or if you have dimensional regularization, you will have some contribution of this type, where epsilon will be power minus d. So when you take d equal to 4 limit to go back to the 4th dimension, you will have some pole, and these two basically will be the divergence relating to different regularization. So we're going to just skip this one, because in this method, basically all the polynomial power law, or the power law divergences, for instance, a divergence of this type, you have some propagator here, whatever, with some power alpha, some power beta. If in the end you end up with some power that is not 0 in dimensional regularization, anyway, you will get something which is 0. Okay, so that you will not see this. You will not see this type of contribution. So let's just go there. But if there are, you should just make extra renormalization to take care of those divergences. We can just avoid them in dimensional regularization. So having said so, the divergences that we should really try to look at and see whether they appear or not are the logarithmic one. And let's start from loop divergences. For instance, let's suppose we just have some graviton loop of this type. And we can say, what are the momenta that enter in this loop diagram? There will be for sure some internal momenta here of the loop in the propagator. Here there will be another one that can depend of internal and external momenta. Let's forget now about dependent here. Let's just say schematically will be another 1 over k square, because you have two propagators, right? In general, you will have something like k squared, k minus p, where p is the external momenta. But at energy, let's say just we have k. And then here, we have the vertex. In this case, we are considering we have a 3 vertex, right? We have 3 gravitons, for instance, but you can also imagine to have the Faddeev of fields here. Let's just imagine we have some gravitons. We should basically, what should we do now? So we have an integral in d for k, because you have one loop. We will have 2 propagators. And now we should try to understand the derivative, so the momenta that are in the vertex, 2 here and 2 here, whether they contribute to internal lines or to external lines. Because when they contribute to internal line, they will contribute also to the integral in k. Instead, if they don't contribute to the internal line, but they are some external momenta, they will basically not enter as they will not enter as a contribution in the integral here. Okay, and of course you can check different cases. Let's suppose that we take as one case, like we suppose that the two momenta that are in the vertex, remember they are two because the vertex only contains only two derivatives. Let's suppose you have an external momenta, one internal momenta, an external momenta, one internal momenta. In this case, you would have something of this type schematically, okay? And basically, you may have something that goes like 1 over k squared for k, and this would give some power law divergence. So we don't care about them in dimensional regularization. But if you were in, for instance, cutoff regularization, you see the divergence would have been proportional, this power law divergence, to two momenta, which means two derivatives. So it would be basically a term proportional to a curvature invariant that has two derivatives. What is this? The Ricci scalar, because the Ricci scalar has two derivatives of the metric. So you would have basically renormalized the G Newton. Or the G Newton. It's a renormalization of the G Newton. In dimensional regularization, you don't care about this because you don't see them. So what is the relevant one in the end? You can also have partly divergences and so on. Let's forget. What is the divergence that is logarithmic? This case is the one that has, for instance, all the vertex momenta that contribute basically as external momenta. And in this case, you would get something in the integral that goes like this, with some four momenta schematically. And this, of course, would be something logarithmic divergent. So in dimensional regularization, there would be something that goes like 1 over epsilon plus stuff, okay? And you would say, okay, now to renormalize this term, I need something in the action that contains four momenta, which means four derivatives. And as Anna said, what will help in this case? What will help is basically symmetries, because we know that whatever we have to write down in the Lagrangian must still preserve diffeomorphism. So we have to write some invariant quantities in terms of curvature and covariant derivatives and metric. And indeed, what happens basically is that these terms will be proportional to curvature squared. So it will be proportional to terms that have four derivatives. It could be like, for instance, there could be an R square, there could be a Ricci square, there could be like many type of terms. Let's just be generic and say basically that what we expect in the one loop divergent action will be anything we have. There will be, let me write here, this will be the 1 over epsilon pole of the divergence. And then there could be, as we said, anything. I will be quick here because Anna already said something. You can imagine to add anything you want that has basically four derivatives acting on the metric. You may have another coefficient here that will be some Riemann. And actually, you could have this Riemann contraction, but in principle, you may ask, could I have another contraction where you take the mixed one, for instance? You have mu nu sigma, and then you have mu nu rho sigma. But actually, these two are related by this type of Young identity. I don't know if it's called Young identity, maybe. Okay, you can use these to basically relate these two. Then you could also have some divergence of this type, right? It's still four derivatives, but this is a covariant derivative. Or you could, but this is the total derivative. So you could also have something like this. This is still two derivative, four derivative, but also this is a covariant derivative. So basically, from what I said, you can already remove these three. up to covariant derivatives. And the other thing that we can use in 4-dimension is basically the so-called Gauss-Bonnet identity, which basically says the following, that this term, I'm just repeating it if someone was not here during Anna's lecture yesterday. This term locally, only locally, not globally, but locally, is a time derivative, so it's a total derivative. Which means that, for instance, when we take variation and so on, we want to compute things and so on, this will never contribute. That's why in 4-dimension, you see, using this, we could write Riemann square as Ricci square plus R square and total derivative. So we do that, and in the end, we will just get a form of the one-loop divergent action, one-loop divergent part of the one-loop effective action, that in 4-dimension will be some coefficient R square plus some coefficient R mu square. Okay, so you see, we didn't do any computation, but we are using power counting and symmetries to really guess the form of the one loop conda term. Okay, but it so happened, as Hannah said, that these terms somehow, at least in Einstein general relativity, they are not important when you have pure gravity. We'll try to say a bit something more here from the perspective of not just on shell physics, but also of shell physics. You see, when you have a divergence, you need to understand whether you can reabsorb this divergence, not only in the couplings and the masses, but also in the field. For instance, let's suppose you have a theory of this type, right? And you get, with this kinetic term, and you get a counter term which has some delta coefficient and box by box. You could still think of like rewrite everything as some all these equal to some, we call it square root of z, okay? Where this square root of z will be proportional to basically 1 plus rho, let me expand, I think over 2, okay? Yeah. So you can imagine that you can reabsorb your divergence in a redefinition of the field. And this is something that is still consistent because you say, okay, let me redefine things in my field. And so I'm reabsorbing things in my field. Now, in the simple example, it's very trivial because you just say, okay, let me just redefine my field in such a way that my divergence can be somehow cancelled, okay? But can we maybe do something like that? Okay, for sure, we cannot renormalize G Newton in gravity because, you know, this is R square, R mu square. So there is no way in which we can say, let's redefine G Newton to cancel these ones. It's impossible. But the question of like, maybe we could make a field, let me call it renormalization or something called field redefinition that maybe can reabsorb this divergence. And what I mean with that is basically just renormalize your G mu nu. Okay, so the G mu nu is just a bare field in general. So it's not the physical field that you're going to use. What we're going to use is the one that is renormalized. Can we renormalize G mu nu in such a way that we can reabsorb the divergence? This is a question you can ask. If it's not okay, then there is no way to renormalize anymore this term. But if the answer is yes, then it means that at one loop, the theory is still renormalizable, at least at one loop. And actually the answer is yes. In pure gravity, you can find a field transformation, or field redefinition, sorry, field definition, or a wave function renormalization maybe, but it's not really the trivial one, that reabsorb this divergence in the field. Why is that? So what I'm saying is the following. Now, the action that we have is this one, plus this contribution. That is, there can also be one loop finite contribution, but we don't care about that. So we have something like this. And they are both, let's say, function of the metric G. Now the question is, can we perturbatively write something like this? So basically, can we define a metric G prime equal to G mu nu plus delta G mu nu such that this can be written? So can we find this transformation, this field definition? Can we find this delta G mu nu that does this? The answer is yes. This can be found. And the reason is that basically this integrand here is proportional to the field equation of Einstein general relativity. That's the main reason. And it will become clear now. But you see, I'm not using the word on shell here. I'm still off shell. I will never go on shell. I will never impose the field equation. Okay? So I'm just saying that this term is proportional to the field equation. Now, which are the field equation of GR in the vacuum? Let's call them, they are G mu nu, right? These are the field equation, but they're not equal to zero. This is, let's say, the operator like this. These are the field equation of GR. Okay? Are these proportional? Well, this is equal to this, right? We can also write, of course, if we define G as the trace of G mu nu, we can also write things in this way. Right. Now, R mu nu appears there, so it means that this and also R will be basically what? R will be minus G. The one loop effective action, the divergent part of the one loop contribution, is proportional to this term. So it's proportional to the field equation. But I'm not imposing field equation. I'm just saying they are proportional to the field equation. Given that, then let's try to see whether we can use this fact to find a delta G that allow this thing, that allow us to write everything this way. So basically, we should take this, we should expand it, and try to see whether we can find delta G that matches this. So what we have to do, we take this, so we will expand it as a for in delta G perturbatively. Plus what you will have, there will be a term which is the first variation of the Einstein-Hilbert action, and I understand why it's important, because these are just the field equation. And then I'm calling this capital delta, the variation of G mu nu. Let's be consistent. Delta G mu nu. Right? And in principle, you can have all the contribution, which may be important, higher loops, but we don't care. That's what you have here. But now the question is, can we have something like this? Can this term be equal to this one? Can I find a delta G that satisfies this? And the answer is yes. Why? Let's just write it a bit better. This one. So this will be delta X. Like this. Then we have this will be just proportional to the field equation, right? And here we have delta G mu nu. Now you see, if we choose as an ansatz to see whether this works or not, delta G mu nu, the transformation, in this way, like capital A, G mu nu R plus capital B R mu nu, this one will be the, what? It will be just the field equation times this combination. Sorry, I forgot R. R. And here we'll have what I wrote there. G mu nu R plus B. Here there is also 1 over 2 kappa square, because in the action there is 1 over kappa square. Let's not forget. I have this one, 1 over 2 kappa square. I have to say this has to be equal to what? To the one loop divergent part. So now the question is, if I can find some A and B such that this relation is true, then it means that I can make a field transformation, a field redefinition, sorry, or a renormalization of the metric field, such that I can reabsorb the divergence in the same starting action, in the same action that I already had. So I don't need to add any counter term to cancel it. Well, it's simple. You just basically do the multiplication here and impose what? That whatever you get here must be equal to this combination here. Let's just skip the steps. It's simple. Just take this product and impose that is equal to this one. And what you will get in the end, you will get that delta G mu nu is equal to, yeah, let's not write anything wrong. But if I take the notes, what's happening just right now? Hello? Can you hear on Zoom? Okay, but how long did you, for how long were you disconnected from us? Must have just. Okay, 1 or 2 minutes. It's fine. Just look at this formula then. So, basically, okay, you can reabsorb the loop divergence if you do this transformation. Okay, that's it. There is really nothing more to say because it took me some time to go there. So, so for sure you listen to that part. Now, what is amazing, actually, I think Toft, that guy, he did like his PhD thesis on Yang-Mills theories in 71, 72, 73. He showed the paper, and 1 year after, he came out also with one loop computation in in GR. So it was really amazing how productive he was in PhD and postdoc. So the thing is that what they did, Toft and Beltman, it's true. Actually, it was, I think, in the lecture notes by Tong from Cambridge, if I don't remember wrongly. At some point, there's a footnote where he says that it's unbelievable how productive Toft was in his first 10 years of research. He did everything that we do today, more or less. So, yeah. So, okay. Dimensional. Yeah, okay. Okay, anyway, let's go to the point. So what Toft and Beltman did basically was, let's work in the Feynman gauge that we considered at the beginning, into the Donder-Feynman gauge. And what they found is that basically the numerical coefficients there are basically A equal to 1 4 pi square 1 over 20, and B minus 4 pi square 7 over 20. Okay? But we didn't need this coefficient to say everything we said. Okay. Fine. But you see, I emphasized they worked in a specific gauge. Indeed, these coefficients are gauge dependent. They depend on the gauge fixing that you use. Okay, and we'll see now something. Before going, if you're continuing, is there any questions? Any question about this? Okay, good. Yeah, maybe you.
They're gauge dependent, but are they scheme independent? Like renormalization scheme independent? Because they're coefficients of marginal interaction, right? R squared and R mu are dimension 4.
Dimension 4, yeah.
So
What do you mean exactly? Like if you change, like if you use like a cutoff or something? Yeah, things can change in principle. Yes. No. The same. Okay. I think just the logarithmic one, yes. I mean, but in general, you will have, if you take cutoff, you will get some extra contribution here. No, sorry, you mean like, if you just focus on this logarithmic one, okay, there will be, whatever you do, either cutoff or 1 over epsilon, you will get whatever you get here, this form with this coefficient. But if you change scheme, you can get extra stuff in the one loop effective action, because you may generate like times proportional to R. So, yeah, maybe the one loop one, the one loop divergent action contains these terms as divergent term only if you work in dimensional organization. If you work, for instance, cutoff, you will also have Ricci scalar plus cosmological constant. And then you have to reabsorb them, but not through a field definition in this case, but through G Newton. Yes. Then, even if you work in dimensional organization and you have a cosmological constant, you can still reabsorb things. Okay. And the way you do it, like if you work purely off shell, you can still make this transformation and so on, and you can reabsorb things in a Newton's constant. If you go on shell, as some people sometimes do, you will set to reabsorb things in the cosmological constant. So this thing. But anyway, the point is that working dimensional organization, either cosmological constant or not, in the starting action, the one loop can be still reabsorbed. I don't know if this really answers your question. But like if you go from a cutoff to 1 over epsilon, you will change really just the log mu equal to 1 over epsilon. That's the only difference you will do basically in the. Yeah. The one loop is gauge dependent. Yeah. Actually, let me say. Yeah. Let me say something quickly. Also, because I mean that's the only thing I know about the gauge dependence of those terms. I will tell you now. They are always gauge dependent. You may ask, what is the relation between? Yeah, okay, that's step by step. So, as I said, if you take the gauge fixing of the Donder, that's what you get with the Feynman choice. But you can ask, if I get So the donder was this one. This was the donder. Okay. This was the donder. Now let's do something. Let's introduce another parameter, omega. So now you have two gauge fixing parameters. You can ask what happened to the divergence. What happens is that the one loop divergent action in dimensional localization will still be something like this. But now this coefficient A and B in general will depend on C and omega. C and omega. Now, what is interesting is that you can find a gauge, which is very, I don't even remember the value of this omega and zeta and C. But there was a paper in the 80s, I think, by Carlos and other people, where they found some value of Xi, let's call them Xi star, and omega star, such that A of omega star and Xi star is equal to 0, and also the other one is equal to 0. What they do basically, do the computation engineering gauge. You get this some expression here. You impose that they are both equal to 0, and you determine which are the Xi and omega that gives you that value. Now there are more than one solution to this equation. Let's not go there. We just say that this is possible. So you see, they are gauge dependent, gauge fixing dependent. So you can choose a gauge where they die, where they're not there anymore. You may ask now, but is there then a relation between this gauge fixing and the field definition? Actually, there is. And maybe one simple way to see that is the following. You see, I'm not going on shell. I'm just off shell, because this is just off shell. I'm not imposing any field equation. But we know that on-shell physics is gauge independent. So for instance, if we take the one loop effective action evaluated to different type of we compute the one loop effective action like for two different choices of the parameters. So let's one is on Xi1 and the other one is omega 1, and the other one will be, so one is Xi1 omega 1, the other one is Xi2 omega 2. Now, the difference here of these two action wait a second. Let's see if things work. We have one loop effective action at two couplings, at two gauge fixing parameter here. One loop effective action with other two gauge fixing parameters. And we are taking the difference, which means that the part that will not be yes, okay, it works. So basically we take this difference. In general, there will be parts that are depending on the gauge fixing and parts that do not depend on the gauge fixing. The part that do not depend on the gauge fixing will go away. What will remain is just the part dependent on the gauge fixing. And since they are not equal because I'm taking different combination of the choice here, there will be something that survives. But since we know that on-shell physics must be independent of the gauge fixing, whatever we get here must be somehow proportional to the field equation, which means that if we impose the field equation, then things must go to 0. So we should expect something of this type, some integral, some function here that in principle we can determine. And here there will be the field equation. Yeah. That's what you should expect if you want that on-shell physics is independent of gauge fixing. Now let's suppose we take omega 2 and omega 0. Sorry, omega 2 and omega 2, xc2 and omega 2 equal to xc star and omega star, and omega star, which are basically the one for which the effective action divergent part vanishes. What will be left, basically, I'm sorry, and then you take the choice of omega 1 and the xc1, the one of Toft and Belton, for instance, just to understand maybe some relation, which was basically 1, 1. Okay, what you will get is basically that the divergent part here with 1, 1 choice will be something equal to what? To an expression that is proportional to the field equation. That is what we found with the Belton and Toft computation. And what was the F mu nu in Toft computation? Well, the F mu nu in Toft computation was basically just delta G mu nu. The transformation is basically we considered. So just, or maybe the minus sign if you invert it, but anyway, it's fine. So you see, so the two things are related somehow. You can see a relation between the two. But this is important. So I never went off shell so far, right? I'm just saying, let's just work off shell. There is something H fixed independent, proportion to field equation, doesn't matter what. In the end, the message is that one loop divergence in pure gravity are not there, just because we can reabsorb. That's why sometimes people say that one loop divergences are renormalizable in gravity, pure gravity.
What you're saying is that if you choose now the psi 1 and omega 1, then you have a different
But
view, and then you have different ones.
yeah, so you will have basically what I'm choosing there exactly is that I'm choosing the A and B of Toft for the first part is 1, and then yeah. So but it's just the same. I mean, yeah, don't get confused. I think I shouldn't have even got here, but I don't know if it's related to what you were saying, more or less. Yeah, Franz. If you want to ask, you can.
Yeah, it's that. So, in this case, if we go on shell, those coefficients are actively gauge independent because it's zero. But the cosmological constant, that's not the case.
No, it's the same. In cosmological constant, you can still do things because you see. Let's see the way you did that you want to go on shell, right? So if you have a cosmological constant, it means that you're starting Lagrangian is this one. Okay? And now you're saying there will be some one loop here. Should go down. There will be some one loop here. There will be C proportional to the field equation. But let's suppose you impose the field equation. As you said, the field equation will be this one. G mu nu lambda. These are the field equation. Lambda C. Let's not confuse with cutoff. This is a cosmological constant. Or so Ricci will be what is this? G mu nu F4 lambda square and R square. So R will be 4 lambda C and R square will be 16 lambda C square. So it doesn't matter what, just you will have some that is proportional to what? To just lambda square with some coefficients, call it C. Okay? Now, this is still fine because you can redefine your lambda C, so renormalize lambda here. Like this. Okay, where C will contain the 1 over epsilon as well. Okay. So basically, we can redefine things in such a way that basically theory is still one loop renormalizable because we are renormalizing also the cosmological constant that you already have in the starting Lagrangian.
And the question would be, let's see, is that gauge independent or independent? It's current shell, right?
Yes, I'm on shell. No, it will be because it will be a combination of these A and B. Yes, yeah. So it will be a combination of these A and B here, which are gauge dependent. Because you went on shell, it canceled. You went on shell, yes, you went on shell. Yeah, right. Thanks, Benjamin. So only when you impose the field equation for real, they will cancel because you went on shell. But even if you stay off shell, you can still try to cancel this term here without going on shell. But in that case, you have to renormalize the cosmology, the Newton constant, because you will have in the transformation the G mu nu, the same stuff there in this transformation, but now there will be the transformation G mu nu that multiplies also a term of this type, because you have it in the field equation, right? And this one will be something proportional to R. So when you have something proportional to R, you can put it in the Newton's constant. Okay, yeah. Okay, anyway, so we are late, let's just... Okay, last point is that it doesn't matter if you go on shell or not, just the fact that you are proportional to the field equation, you can still reabsorb things. Okay, so this is more general, I would say, than say, oh, we are working with scattering matrix, and so they will not contribute, because even off shell, you can show that they do not contribute. Okay. You will not see them.
You don't see any
No.
divergence.
You will not see the, actually, if you do a computation of this graviton scattering here, plus the S2U and the contact term, those terms will not contribute in this theory. Yeah. Yeah. Of course, do the computation, take the on-shell graviton states here and everything. Yeah, they will not contribute automatically. But, okay. Yeah. You may say, what happens if I have matter coupled to gravity to a loop? This doesn't work. So if you have gravity plus matter, theory is one loop not renormalizable. Just because the field equation, so just because the one loop effective action, the divergent part is not proportional anymore to the field equation, because we'll have G mu nu equal to T mu nu. So T mu nu, even if you replace it there will be a T mu nu square that will generate terms, for instance, like box pi square. And these are terms which you will not have in the static Lagrangian, right? Because you have four derivative of the scalar field if you work with scalar fields. But anyway, the point is that only pure gravity is one loop divergent is one loop renormalizable in 4 dimension and without matter. The next thing, of course, you can ask is, for instance, what happens at a loop? The next question. Unfortunately, there's no time because we need to say something else. But okay, let's do this. So at two loop, what is the type of diagram that can contribute? Just to tell you, are some objects like this. With these lines, I just mean anything you want you can put here, like graviton or Faddeev-Popov fields. And then you can attach to it, for instance, 3 on-shell gravitons. You do power counting and so on. In the end, you will see that what happened is that the logarithm divergence come from terms that contains 6 derivatives acting on the metric. And 6 derivatives can be either like terms that have 3 curvature, whatever they are, or terms that have, for instance, I don't know, R, box R, something like this, okay? Anything you want. What happens is, again, there will be terms that are proportional to the field equation, like this one, terms that are proportional to the field equation, like this one, Would be nice to write all of them, but there is no time. They are in the notes. There are many terms you can write down. Let me just say this, that the only one that will not contribute are the ones that are not proportional to field equation, that cannot be reabsorbed by generalizing the transformation that I showed before. And those are the ones that are proportional to the Riemann tensor, cube. And actually, in general, you can have two combinations. You may have this one, and then you may have also something like this, where you contract the mixed one here. Alpha, rho, sigma, beta. Yes, you see these are different because here I'm contracting pairs. Here, no, I'm changing the two here. But you may ask, are these independent? They are not. They are actually dependent. And there is, I never understand how this is called, either Schouten identities or first-like identities. But basically, you see, if you have a tensor with 5 indices, but you're in 4 dimension, and you anti-symmetrize the 5 indices, you get 0, because you don't have enough indices to really and fully get something that is non-zero. Indeed, there is this identity, which is true, just because you see you have 1, 2, 3, 4, 5 indices that you are anti-symmetrizing, so it must be 0. And if you open this identity and so on, you will get basically what? Terms that are proportional to the field equation, and terms that are not, that are of this type. And what you can show is that basically you will have, for instance, this type of combination. You will have 4 times this one, minus 8 times, which one? This one? Yes, because I did there. Yeah. And this you can find also in the book I said by Percacci. And also in the original papers actually by Sagnotti and Gorov. Yes, Gorov and Sagnotti were the first to actually determine the one-loop divergence here. The two-loop divergence completely. Alpha, beta. Plus total derivative. Sorry, not total derivative. Plus the terms that are proportional to the field equation. Let me just write plus equation of motion. Okay? So you see, in the end, you can write things in the effective Lagrangian at two loop just in terms of one of this combination. Let's choose this one. So basically, the two loop effective action in the end will be something like this. There will be a coefficient. Let's call it A. Start with A. A. And then there will be that term. Okay? That's basically the structure of the two-loop divergence. There is nothing else you can expect if you stay here. Gravity. Now, there are two questions to completely fix, you need to answer to completely fix this structure. One is the numerical coefficient. Of course, you need a two-loop computation there. It was done by Sagnotti Gorov. I think it was one of the hardest computations I think has been done in gravity, in Einstein relativity, perturbatively. And the other thing is to determine the order of the divergence, because we are at two loop. So we could ask, do we get 1 over epsilon plus 1 over epsilon square, or we just get 1 over epsilon square, or whatever? I mean, what do we get? Because in a two loop, you may expect both terms to appear in general. And what really happens is that since you don't have, one can show it very easily, but because there is an argument one can give. But since basically you don't have one loop divergences, what will happen basically is that the only pole that will contribute at the loop is the simple one. There will be no double pole. Okay? This is true actually for anyone. If you have a theory which is finite at n loop, up to n loop, then n plus 1 will have only a simple pole. Good. And this was again shown first by Chase, I think, this fact of this 1 over epsilon, and then Sagnotti improved it, I would say. So in the end, if you put coefficient precisely and loop coefficient precisely, what you will get in the end is 1 over epsilon times 209 over 2880 pi square. And this was computed by Gorov Sagnotti, then also by Van Den, I think, after that, and other people, I think, maybe did this computation like in other people, I think, working supergravity also reproduced this. Okay, this end the story of GR, I would say, as possible renormalizable quantum theory, because it's not. So this confirmed the fact that, you see, because we said that by power counting, GR was not renormalizable. Then we found something finite to one loop, and then you would have wondered, okay, maybe there is some cancellation happening at any loop, some magic, and things will be finite. Who knows, maybe we are missing something, but it doesn't look like, because we really have something which is non-zero and is there at the loop in pure gravity. And is this Riemann cube term. And now you can ask, okay, fine. We know that anyway, this is not something bad, because we can do effective field theory of Einstein general relativity. And indeed, yesterday we heard from Anna very nicely that actually we can do computation. We can even compute amplitudes, anything we want, as long as we are in regimes where we can trust the theory. Because as long as we say, I work at some energy scale E, that is below some scale, for sure below Planck mass scale. And up to the scale, we notice that, okay, if I neglect the 3 loop, for instance, the error that I'm committing is small enough that I can neglect it in my experiment, because it's like below the accuracy maybe of my experiment or whatever, then it's fine. You just do experiment with an effective theory of gravity and do whatever you want. And that's, I think, something good to do. And very often I would say that people think that this could be done up to Planck scale, up to the mass Planck, and then maybe at Planck scale something else has to happen. Now, this is not the end of the story of Einstein theory as a normalizable theory, because it could be that there is some non-perturbative normalization, as we'll hear from Benjamin and Alessia. Or it may happen that something else happens, indeed, at Planck scale, like string theory or other approaches, and you will hear also from Ivan about string theory. But my point is that my question I would like to ask in these last 37 minutes, unfortunately, only 37 minutes. Yeah, 37 minutes. Let's do 40. Would like to ask the following question. Can we somehow still make sense of Einstein, Einstein, of gravitational interaction in the framework of perturbative quantum field theory, and still try to satisfy the principles that I wrote down in the first lecture, like locality, unitarity, renormalizability? Because if we manage to still satisfy them, and then we even learn something new about physics, not just about mathematics, it could be something like promising and maybe something more to understand that could be hiding under, behind the corner, right? And that's the point. In the same way, for instance, if you think of like Fermi theory of fermions, when you have like fermion that interact with a conductor, and that theory is not renormalizable. So even there, you will not have the Newton constant, you will have the Fermi constant, and at high energy scale, which is roughly 100 GeV, things break down. But that was not a problem. You will not just say, okay, then we cannot make sense of really renormalizable field theory for weak interaction. No, it's not true, because actually what was noticed there is that if you add extra stuff in the Lagrangian, like a gauge boson and a Higgs field, you can write down a theory of the weak interaction or the electroweak interaction, which is actually renormalizable. Not just renormalizable, but strictly renormalizable. So basically at a high energy, the couplings that govern the UV behavior, basically, are dimensionless. And the question is, can we achieve something similar also with gravity in quantum field theory in 4 dimensions? So trying to be as conservative as possible. Then if things goes very bad, we then move to somewhere else. But if things go nicely in some way, then maybe we can try to understand the open questions better. And this is what we would like to do. Let's make stop 1 minute if there are questions about anything we said about GR.
The combination of Riemann tensor cancel. You were saying that in D4 you have 5 indices tensor.
Oh, the thing is that you see, if you have an antisymmetric object, this object has 5 indices. Okay, in 4 dimension, you only have 4 possible different indices, which is 0, 1, 2, 3. So for instance, if you put 0, 1, 2, 3 here, then here you must again use one of them. But if you use one of them again, this will be 0 because it's totally antisymmetrized. Okay, it's just a matter of how many indices you have in your dimension to really saturate these 5 things. Okay, for instance, if you are in 5 dimension, then you could put a 4 here, and it's fine. Okay, you're welcome.
So you're saying it's equivalent to hit autogravitational pulse?
Yeah. No. This is true. You can prove it only at 2 loop. Yeah. And but as I said, if you have a theory in general that is finite at n loop, also that is finite up to n loop, then the n plus 1 loop will have simple pole. Okay, but here we only know that 1 loop is finite. So at 3 loop, we will have the 2 loop that is not finite. Okay. So what I'm going to talk about now, for people who will also attend the workshop, there will be talks about this theory. So the idea is just to give you the idea of what it is, and then if you want to listen to more specialized things, you go to the talks. Although, yeah, I was planning something. So there is no more questions, right? I can go in the last part. And here I may get emotional because I may get more, because I like this theory. So yeah. Okay, let's. So as I said, this doesn't work. So far, we focused on this theory, which only contained the Einstein-Hilbert part. Okay, let's even put this if you want. But in principle, you can say, okay, can I add something that makes the theory renormalizable? And the answer is yes. So in 4 space-time dimension, if you add all possible terms that contains 4 derivative of the metric, which is exactly the same that we wrote here before going here, let's say. But we know that in 4 dimension, we can just reduce to these 2, okay? Up to boundary terms. If you write this, you get a theory that is power counting strictly renormalizable as any other interaction in the standard model. And I may ask so many questions because, come on, this is what you wrote before. You said that this term can be eliminated. But the thing is that those terms can be eliminated only if your starting Lagrangian is Einstein-Hilbert with its own field equations and its own, let's say, perturbative expansion. But here we have a different theory to start with, which may have different propagators, different vertices, and a different perturbative expansion. So you will not expand anymore around, for instance, the graviton propagator plus things. You will expand around, no, you will not expand anymore around the kinetic operator of Einstein plus things. You will expand around another kinetic operator with other interactions. So that's why, as a starting bare Lagrangian, we have something different. And we would like to understand three things here. Why it is renormalizable, what are the degrees of freedom in the propagator, three, what are the good things, four, which are the things that still need to be understood. So there are four things. But before going on, first of all, sometimes refer to this theory as quadratic gravity, because we are adding something more. I don't know if it's a good name, but let's refer to it as a quadratic gravity. Usually you're doing nothing so unconventional. Just say, let's add the simplest thing you can add, respecting the symmetries, metric compatibility also, and no torsions. You're not putting anything. Parity invariance we are respecting as well. So you have this. But it's more convenient, actually, to write this Lagrangian in terms of another combination. You see, because there is another tensor we can introduce that was introduced yesterday by Anna. I'm not going to write it again, which is the Weil tensor, whose square is just, I think this was also written by Anna, yeah. Whose square is the following. Okay. But then you can also use the Gauss-Bonnet identity. And in the end, you can write, you have two equations to basically choose only two invariants. And you can choose, for instance, Ricci square equal to this plus 1/3 r square plus the Gauss-Bonnet that I wrote before. Maybe still there. Yeah, that one. Plus Gauss-Bonnet. But the Gauss-Bonnet local is a total derivative. So we can forget at least what we're going to say here. It's not important. And you can just write the whole Lagrangian quadratic in terms of r square and Weil square. Why Weil square? Because Weil square is interesting because it will contribute to the spin 2 part, while the r only to the spin 0 part. So we can make the discussion more clear. And for reason it will come more clear soon, I will also choose specific coefficients. And again, let's just imagine that we are in a situation in which cosmology constant is small and negligible, although it's important for renormalizability in general. And let's choose, let me choose with my convention, which is this one. Alpha 6 is a coefficient. I'm just recalling them, redefine them. Then minus beta over 2 c square. This is the Lagrangian, the actions we would like to consider. Again, we can do the same thing. You could say, I take the metric and I start expanding. Okay. And what you will generate this time? Since you have quadratic terms, you will generate not only terms that have two derivatives, but also terms that have four derivatives. For instance, in the kinetic term, there are what? There are terms which are of the type h secondary h, but also terms that have h four derivative h, just because you have this term here. So you see the kinetic term is different from the one of GR. You have extra terms which were not contained in the Einstein-Hilbert expansion of the kinetic term. And you can also have interaction term of the same time. You may have like whatever power here with two derivatives, but also whatever power you want with four derivatives schematically, right? Just because of these terms. So you see, the idea is completely different. And we can ask the following. Oh, we're gonna do that. The same. You can like write down a propagator, you can invert it and so on by doing things correctly. And you can write really what you get for the propagator. Let's just write it. And that's it. We write the propagator. And then we discuss also renormalizability. The propagator is the following. There will be always a gauge, there will be always a part that will be cancelled immediately because of conservation law in the amplitude. There will be a part that will survive. And again, what survives here are the spin 2 projector and the spin 0 projector. But the power in the propagator now will not be 1/p square anymore. Since you have also four derivative, you will get also p to the 4. in the propagator. So what you will get is the following. Let me write it like this, and then we tell you what they are. We will have the spin 2 part. I will not write again the expression, but you remember this one, right? Then there will be p square over p square plus m2 square minus m naught square over 2 plus m naught square plus terms that are not important because they will not contribute even virtually. They're not really important. Okay, so we can remove them. These are, let's say, the off-shell important part of the propagator. And what are these m2 and m0? These are basically related to the coefficient in the Lagrangian. If we call kappa like 1 over p, as we did before, we can just work in terms of the Planck mass. This will be mp square over alpha and no, over beta, sorry. And m0 square will be mp square over alpha. So you see, these coefficients in the Lagrangian, first of all, are related to new degrees of freedom. You have a spin 2 massive degree of freedom and a spin 0 massive degree of freedom on the top of the massless graviton that you have in GR. Indeed, if you decompose these terms in this way, 1 over p square minus p square m square, right? Just the composition of the fraction. I don't know why I'm saying that. But this, what you will get here in the end is the propagator of Einstein-Hilbert plus a spin 0 component minus a spin 2 component. So you see what you have here are 2 plus 1 plus 5 equal to 8 degrees of freedom. So you have extra degrees of freedom in the theory. And that's the reason why you are adding something more. But unlike the standard model where you can add things like by the way you want, more or less, preserving the symmetries, of course, they are there. Here is very restrictive what you can add. Because whatever you have to add has to respect different invariants, and the degrees of freedom may only appear, okay, through these projectors, okay? So the only way to make them appear are like with extra derivatives or extra power of the momenta. You cannot add, for example, another spin 2 the way you want that is not connected to this type of structure, just because of the differential invariance. And you can ask, are these extra ones somehow physical and physical? No, they are massive degrees of freedom. You cannot remove them with any gauge transformation. Okay, they are physical in principle degrees of freedom that will contribute on shell. So you have a new theory with 8 degrees of freedom. More importantly, if you look at the propagator, first of all, you see they have these masses. So you can see that if beta and alpha are large, which is fine because these are normalized parameters. If these are large, then you can have masses which are below Planck scale. So you see, this is completely different from effective field theory, not at Planck scale, even below Planck scale. Because if you have masses which are below Planck scale, you may have new physics appearing already at energy scale of, for instance, 10 to the 13 GeV, which is very high, but still fine. Indeed, I will say something. Okay? Just because in the case of GR, Einstein theory, perturbable expansion, in effective field theory, the coefficients there are usually order 1 or smaller than 1, because you have an effective field theory expansion in that case. While in this case, no. This alpha and beta can be large. You may ask, but if they are large, is the perturbative expansion trustable? Yes, because the perturbative expansion in GR and here are different. If you look at the perturbative expansion here, in this theory, it will actually go the loop at loop level like 1 over alpha and 1 over beta, which means that the large alpha and beta are, the better actually the perturbation theory behaves, which is completely opposite from the effective field theory case, where alpha and beta will contribute only in the numerators, because they will never appear in the denominator. So this is a main difference between the two approaches. Just the perturbative QFT is completely different because you define it in a different way. Completely. You have the different, you are expanding a different Gaussian somehow, right? And these are the new degrees of freedom. You see, you already can think why I'm choosing those coefficients 6 and 2, and why those sign plus alpha and minus beta, because I want basically no coefficient here appearing to not bring them around. And also I want no tachyon. So I want mass squared to be positive. And they are positive. This beta is positive if this alpha is positive, which means if this alpha is positive and this beta is positive. That's why I put the minus sign here to not put a minus sign then in the mass. Okay? Now, as I said, the propagator will behave like 1 over p to the 4, which means for actually perturbation theory and loop diagrams is good because we'll have something more suppressed, right? But also the vertex will have p to the 4, so we may say, okay, no way, that's suppressed, but also the vertex like goes as p to the 4, so things can go bad. But actually, that's not the case. There are different ways to see that. The first thing is that basically, if you look at the couplings that contribute at high energy, what happens basically is that the propagator schematically, let me schematically the propagator, okay, it will have something like this. P squared plus alpha p to the 4 plus beta p to the 4, right, the propagator. And you see, at high energy, okay, what really matters are this part. The same for the interactions. What really matters at energy are the one with p to the 4, which contain only alpha and beta. So the only coupling that matter at energy are dimensionless. Why they are dimensionless? Because basically R square has dimension 4, while square has dimension 4, so alpha and beta have to be dimensionless. So basically, this is strictly normalizable just because we have dimensionless coupling that matter at high energy. But what is important is that your perturbative expansion is not around GR like before, but is around a different theory. So you expand around a different free theory. So you have a free theory, you're adding interaction, and the free theory is different from GR. You have different degrees of freedom, different structure. For instance, if you want to look at an integral with L loops, 1 over k squared, 1 over k to the 4 propagator, E propagator, and then some worst diversion with k to the 4 vertices. This one will behave like 4L minus 4I plus 4V. Using again topological identity, this will basically be k to the 4. So you see you have a divergence that does not get worse if you increase the loops. Which means if it does not get worse when you increase the loops, it means that you do something, you add something to a loop, then the thing that you add, the structure that you add, will be good at any other loop. Okay? Indeed, any loop, two loop, three loop, and so on, perturbatively, will have the same structure of the starting Lagrangian. That's indeed the reason why it's renormalizable. Okay? Now, you see, here there is a minus sign. And this minus sign means that the kinetic term associated with this spin to field has a minus sign, which means, oh, wait, usually I put kinetic term with a plus sign because I want positive energies, right, in the kinetic term. But it has a minus sign. In this is called, I don't know why now, but it's called ghost. But does not have the same meaning of the ghost I mentioned before. Okay, it's completely different. But they're called ghost anyway, in this context, because they have this minus sign in the kinetic term. And usually this ghost can be bad. because ghost with a minus sign, so field with a minus sign, may lead to classical instabilities, because you may have like higher derivative field equations where you may have some growing solution that needs to have some specific boundary condition to behave nicely. Or you may basically see that this minus sign here sometimes can be also be a cause of a violation of unitarity. So before even trying to say that this theory is good, one should really try to mention I mean, you should at least give a prescription how to treat this particle, because if you do the standard things, which means standard optical theorem with the standard Feynman prescription here, I epsilon, and standard things, you will show that the theory basically is not unitary. I will say something soon. So something has to be done, okay? But before going there, let me say that, so the work that are going on now are basically about how to, there are different approaches on how to treat this ghost, okay? And the fact that things, standard things do not apply here in terms of quantization of this field, and the fact that maybe something different has to be done, and we'll mention soon in 5 minutes what it is, something, I would say is not surprising in general, because already if you start from a theory with one derivative, fermions, you quantize them in a certain way. You consider theories with two derivatives, you don't quantize them as fermions. You quantize them in a different way. It's true that there is also the statistic and so on, but still you do something different. Now you have here theories with four derivatives, fields with four derivatives, which are ghosts. Sorry, we have ghost field with a minus sign. Maybe we should quantize also this higher derivative in a different way. Maybe it could be that field equation with different derivatives needs to be quantized in a different way. So in principle, I would not be so worried in saying, okay, maybe this minus sign needs new understanding, because we never see this type of fields in the standard model of particle physics that we usually study in the textbook. And that's the reason why I think it's interesting still to understand why, because this type of action satisfy locality, renormalizability, as any other theory in the standard model, and also unitarity can be satisfied if you change something as compared to standard prescriptions for defining a propagator, for instance, or for defining norms. And here I will be just objective. I will not say anything at the moment what I prefer, what I don't prefer. I'll just tell you what is that has been done so far. But before going on, if there is, I know I've been very sketchy here because unfortunately time is limited, but if there is any question about the propagator and the normalizability, why is the power counting normalizable? If it's not clear, ask me now because we can make it more clear. The reason are two. Well, yeah, I say two, although they're connected. One is that you have a propagator which goes like 1 over k to the 4. One is that you are in 4 dimension. This is important because it is not renormalizable in higher dimension. And 3, the fact that you are in 4 dimension, indeed, tells you that these couplings are dimensionless. Because in higher dimension, they would not be dimensionless. So these are two important things. And indeed, as you can see, basically, dimensionless couplings, loop divergence do not get worse and worse. They stay the same. So basically, we need only one type of counter term, which is the same structure that you have here. Let me just say that for renormalizability, when you renormalize the theory, you also need the boundary term, like the Gauss-Bonnet and so on. You need to add them for the consistency of the normalization, but I'm not writing them. But so there will be a Gauss-Bonnet and a box R, so there are terms that are there. But they will not contribute, for instance, to the propagator and perturbativity to the vertices in 4 dimension. They not contribute. But when you use dimensional realization, you have to take them into account and so on. But anyway, so that's the theory. Now, let me say something nice first about this theory. You see, I mean, it's something simple they're doing. So when people say quantum field theory, Einstein, quantum field theory of gravity, the people always think about Einstein gravity. No, for me, quantum field theory of gravity is quantum field theory of gravity. Gravity does not need to be Einstein gravity. But then if you say when a quantum field theory is renormalizable, as any other theory in standard model, then for me, this is the theory. Why this is the theory? Because in 4 dimensions, if you assume no torsion, metric compatibility, no parity, violating time, and so on, this is a unique Lagrangian that you can write down. There is nothing else except boundary terms. There. Okay? It's unique. It's more unique than what, because in the standard model, you still have freedom to add field and so on. Here in gravity, you cannot add anything unless you give up torsion freeness and metric compatibility. That's what it is. The symmetry are very restrictive. So it means that if you do an experiment and you check that this theory is wrong, then you go back and you really definitely give up perturbative renormalizability as a criterion to select theories. But until then, in my opinion, the criterion of strict renormalizability is still allowed, is still powerful, is still predictive, and I think it's most predictive you have at the moment in terms of theories of quantum gravity. And that's the reason I'm going to say. Predictivity and uniqueness are very important, because if you have too many possibilities, it's not good, because how can you even falsify all these possibilities? Here you have one possibility. If it doesn't work, you go back and you change the starting principle. But if you would have like 3, 4, 5 possibilities, then one doesn't work, try the other, but still keep the same principle. This is an infinite game. We should have a unique way to proceed. And that's why here we can do that. I'm not saying this must be the theory that describes physics everywhere you want. I'm just saying that as long as a framework works, let's try to see until it works, but also trying to look at experiments. Because usually we do quantum gravity, and we say, okay, quantum gravity, no, there is no experiment that can guide us. In the 70s, when people were going crazy with the interaction of the standard model, they were helped by the experiments. Otherwise, they will never be able to end up with the standard model of particle physics. But in gravity, people usually say, we don't have experiment. I think there is still some experiment that can say something. Why? Because you have heard of inflation. You will hear more from Zdravan in his lecture. We know that in the sky, we receive radiation from photons and so on. We see photons from the cosmic, from CMB radiation, cosmic microwave background. And we also know that from there, we can see that there are anisotropies. And these anisotropies somehow have to be explained some way. And usually the way is to add something to the Einstein-Hilbert Lagrangian, like for instance, scalar field with some potential. There's a paper called Encyclopedia of Inflationary Models. There are like 300 different models with most of the case, no principle really that is guiding you to choose the model. But phenomenologically, we can explain inflation by introducing something. In a theory of gravity like this, you see, you are asking at the theory level a principle to be satisfied, which is renormalizability, perturbative renormalizability, and strict renormalizability. Because if you ask for super renormalizability, you will get lots of possibilities. It's not good. This is the only strict renormalizability with dimensionless coupling. If you ask for strict renormalizability, you get this. And then the next question to ask, okay, is, okay, I will go back here soon, but you have this theory. Let's suppose you make sense of unitarity by changing something. People may not like what you change, but you change it. Consistently, you try to make something consistent, something that is consistent. But let's try to see also whether we can do something physically at the level of observation. What is amazing is that for free, from this term, you get a scalar field, which is a spin zero, as I wrote there. Okay? And indeed, if you use this part of the action to describe early universe cosmology, you can get, at the moment, the best fit for inflation and CB anisotropies. It's the best in terms of fit explained, in terms of Higgs inflation, Zdravan will say more, I think, but in terms of guiding principles, you are getting an extra term to explain new physics beyond GR. Indeed, if you choose alpha of the order of 10 to the 10, which means from the relation mp squared over alpha, that the mass is roughly of this field 10 to the 13 GV, you can describe new physics beyond Einstein's relativity. Not only that, is new physics below Planck scale. So 13 GV and 10 to the 18 GV is 5 order of magnitude. So we are very sub-Planckian. And we are getting new physics motivated by what? By principles of quantum field theory. It's true that it's not, I would say, like prediction, measurement of quantum gravity. No, we are not. We are just testing the framework of quantum field theory, and this is amazing because just by requiring principle of quantum field theory, you get something that we can also use to do experiment. So once I got to know this, and people say, oh, listen, up to here, this works very well. I said, hold on. If up to here works very well, and this also satisfies renormalizability, maybe there could be, in principle, something more with the renormalizability to understand. So what are the things to do now? Some people say, okay, no, there is a ghost, or I don't want to do perturbative things because I know that a Planck scale, maybe something else must happen. Something can happen. I'm not saying that this is the end of the story. I'm just saying that up to now, the tool we have tell us that we can still do this in quantum field theory, and it's fine. Maybe there should be something more. It's fine also that. But sub-Planckian physics for sure is affected by this theory. And whatever you do, I believe that should be taken into account by their approaches, because this is the simplest explanation you can have. If you go back to the 70s and some people would write down the standard model and someone else something more complicated and say, no, listen, yours maybe is too simple and there's something to understand, let's give up. Let's do something else. No, we should, in my opinion, still try to understand this type of theory. What does that mean? It works very well. Now let's try to also understand this part better. Because it could be that there is something more to understand that we never understood so far, because we never had to deal with ghosts. And actually, in the last years, there has been lots of work going on about ghost fields in this theory. Ghost field, I mean, this spin-2 mass field in this theory. Okay? But you see, what is amazing again is that there is, I would say, still not only theoretical guiding principle, but if you really try to be more open-minded, there is some way to also say, okay, let's a bit follow history sometimes because it's useful. Many times quantum field theory went into crisis, and there were things that were understood after trying other approaches as well. That's something similar maybe can happen here. Who knows? There is something to understand that will work up to some point, and maybe also this one has to be improved at some point. But up to here, it works.
Apart from inflation, that it's a nice fit of R squared, are there any other, I don't know, experimental signature that spoils other technology?
So what I want to say is that, for instance, there is this term. Before going to the consistency of this term, you may say, how does this affect? This is a spin-2. How does it affect inflationary cosmology? By touching the gravitational wave spectrum, the primordial gravitational wave spectrum. You will hear more from Sravan. But what is amazing is that in cosmology, you have a quantity that people hope to measure in within 10 years, which is the 10 to the square ratio, which is the ratio between the power spectrum tensorial over the power spectrum scalar. These are not the spin projectors. These are just power spectrum. PNS. I'm using some letter, but and so far the experimental bound is 10 to the -2. There has been no measurement of this. It's just 10 to -2. Okay? If you just look Starobinsky model, Starobinsky, which is just basically R plus R squared, is roughly 10 to the -3. Actually, it's very close. It may be that in 10 years, people can test this prediction. But if you add this, which I will believe will just slightly change the Starobinsky one, if you add that, you get the following expression. You will get 24 over number of e-folds square, m2 square over 2 m0 square plus 2 m2 square. Okay, that's the formula. If you take the limit of m2 going to infinity, you recover Starobinsky, which is basically 12 over n e-fold square. You will hear what are these things in talk by Sravan. I'm not an expert. But again, you get a formula for this. So it means that if you make a measurement of R, you have direct access to M2, which means direct access to beta, so you can fit it experimentally. Okay, this is something important. Actually, some approaches to try to deal with this ghost, they also find some constraint on this beta, which means that if you do an experiment and that constraint is not satisfied, then you take the theory and the approach, you throw it away, which is good. It's falsifiable. That's what we want. We want theories that are falsifiable. Now, where goes my more personal thing? I do think that this something that will be tested and will give some value for R and will be still, I would say, a confirmation in favor of the strict normalizability criterion. But you see, in case you get an R that is very small, which means an M2 very small, if an M2 is very small, this mass M2, it may happen that it's so small that you will violate solar system observation. If that happens, it's also good, because then you take the theory and throw it away. And you give up for real the strict normalizability principle. Okay? But this is something that can be done with experiments. That's why I think it's very, very important. I know, Benjamin, it's almost, well, I do 2 minutes. 2 minutes. Okay. 1 minute. Okay, 1 minute, 1 minute. Let me just tell you quickly one thing. So you see, this was everything good. If you want to hear more about the open questions, what is the thing? Why these things violates unitarity? Let me tell you that. If in general, why they violate unitarity if you standard things? You see, if you have 1 over p square minus I epsilon, you take this propagator, which is the one for the spin 2, for instance, okay? You quantize it with the same prescription epsilon epsilon, and you compute an imaginary part. We know that from the optical theorem, the imaginary part must be positive. But if you compute it here, what you get is something like this, just at 3 level. There's a stupid example. There is a minus sign, so we'll give you something that is not positive definite. So that's why you are in clash with the optical theorem. But what has been done in the literature? There are different things. Remember, this has to be positive if the right-hand side of the optical theorem is positive. But it could happen it could happen that if you change something, things can change. What you could change, for instance, you could say that the prescription here of the propagator will not be a minus epsilon, but will be a plus epsilon. So we just took the anti-Feynman, which introduced violation of causality at the scales of the mass of the ghost. So you will take a propagator for the cost of this type. If you do that, of course, then you will get a plus sign here. And then, of course, you have to give prescription at higher loop how this works. What you can do is that you can still keep the Feynman with the minus epsilon here, but then you can accept the presence of negative norm on the right-hand side. Do you remember at the beginning I said there were those Cn coefficients in the completeness relation? If you take some Cn that is negative, which are the norm states associated with the ghost, you can still have the optical theorem satisfied. And another thing to do is basically to just change the prescription. Okay, sometimes people call it Feynman prescription, because you make the particle fake. In such a way that you don't use Feynman, you use anti-Feynman, use an average of the two, in such a way that on shell, this ghost never appears. And basically, it's like if it has 0 norm. But it's not correct to say this, but it's like it never appears on shell, so we'll get 0 equal to 0, still something satisfied. And also in that case, you have to give higher loop prescriptions. Now, I think even in these cases, although some people may think that the game is closed, no, I think there is still something to understand. And it may be that in the end, there will be no good solution to this, because I think there is still something to understand about the ghost. Unfortunately, I don't have time to tell you what I think is something to understand, but we can discuss after. I know I'm late, but I want to say just 1 more minute, one thing. This, even if it works, you find some, you will hear during the workshop, if you hear, there will be approaches on it. There will be like Anselmi talking about this. There will be, don't you follow this approach? This one is like Alberto Salvia, Bobo Holdom. Yeah, I can tell you more if you ask me. The main point is that even if this works, and then everything is fantastic, we make sense of this theory, this does not mean that this is the end of the story, because, we cannot say this is the end of the theory. No, it could be that still we need maybe something at Planck scale has to happen with string theory, or some non-perturbative stuff is needed. Who knows? The point here is that even in some Planckian, there is something to understand. And if you do that, you get something which is useful. And if you think a bit of history of quantum field theory, I think quantum field theory went to crisis many times in the past. Because in the 40s, when people were going crazy with infinities, the previous generation, like Bohr and people, Oppenheimer, They thought, no, there should be some new revolution here. Because this infinity is even in Dirac, there should be some new revolution because infinity cannot be right. No, actually it was understood that there is a renormalization theory which helps to understand how to treat with these infinities. Not only that, renormalizability is a criteria to select theories, and this was understood by Dyson. So in the 40s, it was understood that quantity field theory didn't have problem with infinities. Then in the 70s, all the crises happened, I would say, both for weak and strong interactions. Okay, people think this guy, Veltman, he was the only one who was really going deep inside Young-Mills theory, doing wrong things and understanding how to treat the massive, massless limit and so on. He was the only one. People in that time were doing other things. So no, quantum theory Young-Mills cannot work, we should do something else. But no, then was understood that these theories are renormalizable if you do something. Strong interaction. Strong interaction the same. People were leaving everything. They were giving up quantum field theory, but in the end they realized that quantum field theory again had something to understand, there was something hiding in quantum field theory that was understood. Anomaly is the same. It's amazing that there is anomaly cancellation that was understood later. So I'm saying those years there were crazy crises happening, and anyway there were solutions in the frame of quantum field theory. It could be that maybe something similar happened with gravity, where the perturbative quantum field theory framework is still useful for something, but it still needs, some improvement anyway. So with this, I think it's time to close. There will be a gong show again, but if there are questions before going to lunch, please ask. Thank you very much.